Konigsberg is an old Russian town in which a river runs through. 7 bridges connect each island to each other and to the river banks. It used to be a common pastime for local people to go out for a day and to walk over each bridge once, and only once. We will represent each island and riverbank as a letter, so A, B, C, and D. So say if we wanted to give this a go and see if we could visit each ridge once and only once. So we'll start at D and go up to B. We'll go down to island A and then to island D, down to C, up to A again and up to B. We still have an AC bridge remaining. Whichever combination you try and do this with, you will still have at least one bridge remaining at the end. A Swiss mathematician called Leonhard Euler attempted to explain this dilemma. He replaced each mass of land with a single point, called a node, and each bridge with a curve. Euler says that either he needs to find an 8-letter sequence that satisfies the problem, or he needs to prove that no such sequence exists. He does this by looking at a much simpler example of land masses and bridges. Euler then explains that if one of these land masses has an odd number of bridges, then you can work out how many times this landmass will be crossed. He does this by proving that if a node has an odd number of edges, you can calculate the number of times this node occurs. He proves this by adding 1 to the number of edges and then dividing by 2. For example, node A, which has 5 edges linking it, must be used 3 times and thus represent 3 letters in the sequence. Using this fact, Euler solves the Konigsberg bridge problem because if node A is used 3 times and nodes B, C and D are used twice, then by recalculating the total sum, 3 for A, 2 for B, 2 for C and 2 for D is equal to 9, thus causing a contradiction, as Euler already stated that there must only be 8 occurrences for the 7 bridges, therefore making it impossible to travel the bridges in the city of Konigsberg once and only once. What we can draw from Euler's findings are that any graph with more than 2 odd nodes will not be traversable. Secondly, each graph will have an even number of nodes with an odd number of curves emanating from them. Some contemporary uses of this way of solving problems includes being used in topology for the creation of GPS maps, in computer science for the organization of data, and also in various large-scale planning ideas, for example train tracks or road planning, in order to increase efficiency and minimize costs. We chose to investigate the bridges of Konigsberg as it represents how such a simple problem can spark a whole new realm of mathematics, opening up new possibilities in science and technology. Connection.